Hi folks, welcome to lecture 4. In this lecture we're going to take a look at the other general linear equation, which is given here on this first slide. Y minus y1 is m times x minus x1. Now, we usually use this equation when we're given our data in the form of points like this. We might be given just 2 points, that's enough to get us going. We might be given several points, or otherwise our data might be presented as a table, and we can turn our table into coordinates as before. But essentially with this one, guys, we generally don't have a graph, and in that case this is the most appropriate formula to use to determine the linear function governing the relationship between the variables. So this is our function again, general equation of a line 2. The first one was y is equal to mx plus c. That's what we covered in the last lecture. So if we're only given more limited information than a graph, if we're only given 2 points, 2 state points often they're called, we have to use a different approach, which is what we're now looking at. So first of all, we always need to determine what's the input, what's the output. The input is what we control or change, and then we measure the output, what happens when we change the input. So important, guys, to understand that relationship. Input goes on your x-axis, doesn't matter what it's called. Output goes on your y-axis. If time is part of your experiment, time usually is an input. So then, once we know our 2 points, we can determine the slope of the line. And then once we know this slope, we can choose either of the points and feed them into the function. We know the slope. This is our point, x1, y1. And then we can determine the function governing the relationship. So first we just take a look at that slope. If we know 2 points on a line. So here's our 2 points. The rise, guys, is here. What's the delta y? The change in y is the difference between y2 minus y1, and the change in x is x2 minus x1. So it's still rise over run, only it now looks a bit different. Usually you won't have a graph, guys, so it's really important to be very careful with your signs, because a small slip up with any one of these variables or your calculation can very easily turn a positive slope into a negative slope. And like I said in the last slide, that's it's pretty much a catastrophic error. Anything you do with that function from there on in will be utterly meaningless. So you gotta get the slope right. So we take a look. So if we have 2 points here, 2, 7 and 5, 1, these might have been derived experimentally. First thing, guys, always label your 2 points. That's so important. It's so easy to ignore this step and then continually make mistakes all the way through the rest of this section of the module. So strongly advise you to label your points and then feed them correctly into the formula. So y2, 1 minus y1, 7 over x2 minus x1. Be careful with your signs, that's minus 6 on the top. So the slope in this case is minus 2. And like we said, guys, we've no graph to kind of intuitively guide us which way does our line look like. So now you guys pause the video and have a wee go at this one here. Again, be very careful with your minuses. So in the coming lectures we're going to meet many functions which plot as curves, not as straight lines. And very often we're only interested in the rate of change. We might necessarily know, well, what's the value of y at a particular time. We mightn't be so interested in that, but what we might be interested in is, it's not so much here's a point xy. What a scientist usually isn't interested in is, well, what's y? What he's usually interested in is my value increasing from here or is it decreasing? What's happening at xy? What's the rate of change at this particular point? And anywhere where you see the word rate, you can be sure we're looking at a slope. So say we have a rough curve like this, and we're interested in what's the rate of change at this point. What you do is you have to draw a tangent. So a tangent only touches at the point of interest. And then, guys, we can pick any 2 points off our tangent and find our slope from there, either using delta y over delta x or the slope formula we just discussed. So the value of the slope, that's the rate. And again, so anywhere where you see the word rate, guys, you can be fairly sure you're looking at some version of the slope. Huge part of science. So now here, determine the slope of this curve at the point x is equal to -1. Now, if I was really cruel, I'd get you to draw the curve first of all. But we have the curve here. And we're interested in, well, what's the slope at this point here? So we draw a tangent at that point. And then we just pick 2 values. So I've kind of done all the hard work for you guys. What I need you to do now is determine what's the slope of the tangent at that point. And once we know the slope of the tangent at that point, guys, now we know what's going on, what's the rate of change at that point. And I hope it's obvious then, guys, that at every point on this curve, the slope is continually changing. Here on the right hand side it's positive, on the left hand side it's negative. So on most curves the slope, even if you move a centimeter, a micrometer away, the slope changes infinitesimally. So on a curve your rate of change is continually changing. So I let you guys have a go at that one. Determine the slope of that tangent at the point of interest, x is -1. And now we're going to move on, guys, to more than just finding the slope. We're going to try and find the equation of the line passing through these 2 points. So again, label them x1, y1, x2, y2. We're going to find the slope first of all, and then we're going to find the equation. So to find the slope, feed the values in. Again, be really careful. Watch the minus there, see how it appears here inside brackets. So on the top here we're going to have 2, and on the bottom we're going to have 4. So the slope is a half. Now, guys, I can pick either point to feed in. But I'm going to pick this point here because it doesn't have a negative sign. Negative signs always make your life difficult. A 0, guys, is always your friend. So if a point has a 0 in it, that would always draw me towards using that point, because a 0 just makes your life a lot easier. So we're going to use 3 and 6 as x1, y1. Don't worry, guys, about the labeling as in, oh, this is x2, y2. It doesn't matter. As long as you pick one point, feed those values in. Now here, I need to do a little bit of manipulation. To get rid of the half here, guys, I multiply both sides by 2. So that gets rid of the half on the right hand side and the 2 appears. Now make sure you put brackets around the left hand side before you multiply by 2. Multiply out our brackets. And finally then bring the 12 over to the right hand side, add 12 to both sides. And now we have the equation which draws a line Sorry, it's the equation of the line between those 2 points. So here's one for you guys to try. Again, label, find your slope, and then feed your values, your slope value and one of those points into this equation, and that'll give you the equation of your line. Now we're going to look at some practical examples of this. So the freezing point and the boiling point of water, these are called state points. They're measured using a Celsius thermometer and a Fahrenheit thermometer. So essentially, guys, we have 2 beakers, one with freezing water in it and the 2 thermometers, and then we have another one with boiling water. Sorry, not very good drawing. And again, we have 2 thermometers in there as well. So one is Celsius, so this is freezing, and this is boiling water. And we're measuring the state point of freezing. We get a Celsius and a Fahrenheit reading, and the same for boiling water. So our freezing experiment reads 0 degrees Celsius and 32 Fahrenheit, and our boiling point experiment yields 100 degrees on our Celsius thermometer and 212 on our Fahrenheit thermometer. So use this information to develop a function which converts Celsius into Fahrenheit. So we now, guys, this is the critical part. What we have to do now is create 2 points. But the question determines what goes where. Which one is X and which one is Y? Is Celsius X or is Fahrenheit X? But hopefully now remember, guys, we're looking at the 2 points. We're not putting the 2 Celsius values in one bracket and the Fahrenheit values in another. One of these brackets represents freezing and the other one represents boiling. But what's critical, guys, is from the question to determine, well, which is my input? So here, guys, we're converting Celsius. So if we know a Celsius value, we can then determine what the Fahrenheit is. So Fahrenheit is our output and Celsius is our input. We want to be able to have an output of Fahrenheit from whatever Celsius value we input. And most of the marks, well, not most of the marks, guys, but a considerable amount of marks go on getting that right. If you get that wrong, you're going to be guaranteed to be getting not very little marks, but you won't be getting any more than a quarter marks for the question, even if you do it perfectly, because you've completely misinterpreted what's been asked. So here, guys, Celsius is the input. 0 degrees Celsius is freezing. It's the same as 32 Fahrenheit. Here's our boiling point. Again, Celsius is on the left, Fahrenheit on the right. Label them. And I'm going to stick with this label, and guys, I don't use this label again until the very end. So don't write it as F2 minus F1 over C2 minus C1, even though that's what you're doing, because your brain will struggle with it. Stick to what you know. So there's our slope developing. When we work this out, guys, it's 180 over 10, which is 9 over 5 once we cancel. So our slope is 9 over 5. Just remind us of our 2 points. Now we're going to find the equation, or determine the function. There's our slope. And I'm choosing this point because it's got a 0, like I said earlier. So when we feed these values in, y minus 32 is equal to 9 over 5x minus 0. Multiply out the bracket on the right hand side, we just get 9 over 5x. And then, guys, I'm going to move the 32 over. So 9 over 5 by 0, guys, that just disappears. That's why we like 0. So I'm going to add 32 to both sides. Finally now guys, we're nearly there. That's the equation of the function using x and y, but we need to relate it to the system we're examining, which is Celsius and Fahrenheit. Celsius is the input, Fahrenheit is the output. So instead of x, we write in C for Celsius. Instead of y, we write F for Fahrenheit. And you might recognize this as the function we used last semester when we were looking at the relationship between Celsius and Fahrenheit. And that, guys, is how an awful lot of these functions are arrived at, simply experimentally. So now, problem for you guys. And this time, we've got three thermometers. We have a Fahrenheit thermometer, we have a Celsius thermometer, and we have this new one, a Kelvin thermometer. So I think you probably met Kelvin. He's actually Belfast. He was from Belfast, Lord Kelvin. Very famous kind of scientist back in his day. There's also another, so Celsius and Kelvin are very closely related. There's a difference of 273.15. And there's similarly then, guys, there's another one, there's the Rankine thermometer as well, and that's very closely related to Fahrenheit, but we don't have this one in our diagram. So really there's 4 different temperature scales, and we can use this method to determine the relationship between any two of the 3 thermometers presented. So in this case, guys, I'm asking you to develop a function which converts Fahrenheit into Kelvin. And now keep all your values as rational terms. So we'll take a look. So I'm just going to set it up for you guys because I know these are kind of a bit tricky to get your heads around at the start. So I'm not just going to throw you in at the deep end. We'll take you in at the shallow end and then push you out to the deep end gently. So in the next slide, guys, I've just got it set up to help you along, but you still have to finish out the problem. So identify your input and output. Well, we're wanting to change Fahrenheit into Kelvin. So Fahrenheit is the input, Kelvin is the output. So we then we'll go, here's Kelvin, so we can pick, there's my freezing points, and there's my boiling points. And Fahrenheit is going to be on the left and Kelvin is going to be on the right. That, guys, the order is dictated by the question. If I wanted to change Kelvin into Fahrenheit, the other way around, then I'd have to write my points with Kelvin as my input. That's capital K in both cases. And Fahrenheit as my output. But this is the question is asking us Fahrenheit into Kelvin. Once you've got that correct, guys, then the process is the exact same as we've done before. So it's so crucial to identify the input. And then what's my output? In this case, Kelvin is the output. Get your slope. And then use the equation. And as it said on the previous slide, guys, don't bring your values to decimals. Make sure everything stays as a fraction. You're going to get some weird numbers in there. But if you take a look, there's some fairly weird numbers going on in here, so that's going to be expected. So keep all your fractions, guys. Don't dive for the calculator, otherwise you won't get the marks for the question. And take your time. This is the basis really of linear functions. This so much stuff, guys, hangs on this. Any kind of linear regression, be it in statistics, be it in analysis, all falls back to this technique. Going to take a look at another scientific example, diseased mice. I'll let you read the problem. So first of all, the word linearly, that tells you the type of function we're dealing with. We're dealing with a linear function. So there was 8 diseased mice after 4 days and 14 diseased mice after 6 days. So we can see obviously the disease is spreading amongst the mice as time increases. Write an equation which will give the number of diseased mice after any given day. How many mice will be infected after 9 days? And if there was 40 mice in the cage, how long before they are all infected? So all question B and question C obviously depend on us nailing down question part A first of all. So write an equation. So now what you have to do, guys, is look at the question and go, well, what's my input? What's my output? We have diseased mice and we have time. And really time, guys, obviously the person, whoever's doing this test or whatever, he's decided to check the mice every day. He could have checked them every hour. So what's been controlled in this case is the time interval. What's been measured is the number of diseased mice. So that's my input. Time is my input and mice is my output. That's just what I have here. Write down the 2 state points in this format. Well, after 4 days there was 8 diseased mice. After 6 days there was 14 diseased mice. And once you're there, guys, off you go. Same process. Get the slope, feed this new slope value in one of these points into the other formula, and our answer will appear. Is our slope formula. So the slope is 3. And what that 3, guys, means, remember what's on top. Top is the number of mice. What's on the bottom? Days. So essentially there's 3 mice per day. That's what the slope is telling us, that's the rate of infection, 3 mice per day. It's always really a good idea to pause at this stage once you have the slope and try and figure out what actually have I got here. You know, what does slope mean? In this case it's mice per day. So use our slope, and I'm going to pick the 4-8 point to feed in. Multiply out your brackets. Be very careful. So often with the simple stuff, guys, the mistakes are made. Not changing signs as you move values across the equal sign. It's kind of the little things that will always trip you up in maths. So I'm going to add 8 to both sides to move the 8 from the left hand side. And now this is my general function using x and y. I always stay with x and y, guys, until the very last line. So now going back up here, x is day, and y is diseased mice. So there's the function that relates time passed to number of diseased mice. Once you have that now, it's quite straightforward to answer part B and part C. After 9 days, very straightforward. We don't know how many mice are, but we don't need to manipulate anything. It's just feed 9 in for D. So after 9 days, there'd be 23 infected mice. Part C, if there was 40 mice, how long before they're all infected? Well, now we have to manipulate, because we know this value, but we don't know this value, D. So we need to isolate D. First thing I'm going to do is move the 4 over, add 4 to both sides, and then, guys, divide both sides by 3. Remember to put brackets around this, don't just divide one bit, everything gets divided by 3. So now we've isolated D. We're told M is equal to 40. Feed that value in. And we can see then 14.7. You could say 15 days. After 15 days, all 40 mice would expect to be infected. Obviously, they all get completely better again. It was only a mild infection, and they all lived happy, healthy lives. So no mice were hurt in making this video. So now here's one for you guys to try. So here we're looking at a lesion. A lesion is kind of a blemish or a mark on the skin. They're usually pretty ugly, but it's kind of it's usually a sign that something's wrong. If you wake up one day and you've got a big red sore mark on you, you can tell something has gone wrong somewhere. So this lesion, now the diameter of the lesion, so essentially the lesion will get bigger as time passes, but the diameter increases linearly. So that's what the doctor measures. And why we say the diameter, guys, because say for a doctor, like, it's quite hard, unless you really know what you're doing, it's quite hard to measure the area of the lesion. That, you know, but it's very easy for a doctor. He just needs the calipers. He can measure the diameter quite easily. So that's why we would measure the diameter. Here's a picture of a lesion. So the doctor would simply measure what's the diameter of the lesion, and then you'd come back a while later and you could measure it again. So a patient presents. So this is the first measurement that's taken, guys. This is a really important point. Is the first measurement you take in any kind of an experiment is usually t is equal to 0. So a patient presents and showing typical symptoms, and a lesion is measured at 1.6 millimeters in diameter. 14 days later, the same lesion has a diameter of 5.8 mils. So write a function that will relate diameter of the lesion to time. Exactly as we did before, guys, you need to set up your 2 points. What's my input? What's my output? Give you a clue, same as the last one for the input, time. Once you've developed that function, make sure you use the right letters. Once we have established that function, guys, use it to determine the diameter of the lesion after 4 weeks. Everything up till now, guys, has been in days, so you probably will have to change the 4 weeks into days. And use this function to predict when the patient was initially infected. So one thing, guys, is make sure when you're working out this function, make sure you use days for time. Don't use weeks, because that's what I'll be programming into Moodle, is that you use days. Okay, so be careful there. Make sure time is in days when you're setting up your function. So use this function to predict when the patient was initially affected. So I'll just quickly draw a little graph just into a review there. Yeah, I'll just draw it here. So what you're going to get, guys, if we were to draw this graph, at t is equal to 0, the patient shows up and his lesion is 1.6. 14 days later, it's now, I can't remember, 5.2 or something like that. 5.8. So you can convert both of these into state points. Now, once you've done all that, guys, what we're actually looking for is, when did the lesion first appear? Now, if you read back on the question, so when was the lesion 0? When was the diameter of the lesion 0? In other words, when did it first appear? The person then was infected 5 days before the lesion first appeared. So this value is going to be negative, whatever you work out this for. And then add 5 days, because t is equal to 0, we're talking about time before the person first presented. So what you want to figure out here, say if it's 20, if you end up with an answer of minus 20, that basically means the person was infected 20 days before they first showed up to the doctor. Now this is very important, guys. It's exactly like contact tracing that you're hearing so much about, because you'd want to be asking the person who says, well, where were you 20 to now? 20 is not the right answer, guys, just in case you're, but that's what the contact tracer will be asking. Well, 20 days ago, where were you? Who were you in touch with? Etc. Especially if the lesion is associated with an infectious disease. The process, guys, is exactly the same as we've done on the previous slides. So that, guys, kind of finishes up the lectures really for linear functions. Just to give you a quick review of the really important bits before we disappear. The slope is the most important part, and most particularly the nature of the slope. Is it positive or negative? In terms of a real world function, slope is called rate of change or just the rate. So anywhere where you see the word rate, you're looking for the slope. An uphill slope is positive, a downhill slope is negative. A horizontal slope has a slope of 0, and a vertical slope, often they could say it's got an infinity slope. That's meant to be an infinity symbol. Or else they say it's undefined. The reason why it's undefined, guys, is y2 minus y1. You can see, guys, x2 minus x1, there's no change in the x values in a vertical line. So that's going to give you 0 on the bottom. So that's why they say it's undefined. You cannot find a value that's got a 0 on the bottom of a rational term, of a fraction. So that's what we mean when we say the slope is undefined. So in this course, guys, we're definitely going to come across these 3 slopes. We generally don't come across these ones. The reason is, anyone, is because these are not a function. Vertical line, remember, is going to, so one input has, in this case, an infinite number of outputs. Doesn't really occur in science, so we generally don't deal with vertical slopes in science. Certainly not in this module anyway, just to be a bit more specific. The slope can be determined visually, like in lecture 3. What's the change, what's the rise over the run? Or using the slope formula if we know 2 points or 2 state points, 2 pieces of data from our system. If we're given the graph, we use y is equal to mx plus c. The slope, again, it's more of a visual exercise. Change in y over change in x. Y-intercept then is where the graph cuts the y-axis, So you find c visually, and then you try and find your slope visually as well. Personally, I always prefer this equation. It's much less likely, you're much less likely to make a mistake because you can see everything in front of you. You can see the y-intercept, you can see the slope is positive. So straight away, that's 2 out of 3 things. We can see this usually, and we can see the nature of the slope. Is it plus or minus? And the only maths then is calculating what actually is the rise over the run. So like it says, use this function when you're given the graph or when you're given a scenario with a fixed part and a variable part, like the taxi, the waste, etc., the waste collection. This is a quick review of today's lecture. If we're given 2 points, we use this function. Slope, using our slope formula. Choose the slope and either of our 2 points. Possible to avoid negative values. 0 makes your life easier here. So use this function when you have 2 or more points. So that finishes us off, guys, for this lecture. So thanks again for listening, and we shall chat to you for the next one very shortly, where we'll be looking at quadratic functions. So it's the second. So this is the first of our 7 functions put to bed. We will be coming back to linear functions again every now and then, just because, like I said, it's our preferred method of analysing curves. And similarly, like I was saying, if you need to draw a tangent to a curve, we're back to using these methods again to analyse the tangent to determine the rate of change at any point of interest. So thanks again, guys. I'll stop now and we shall chat to you shortly.